Go.
Hi, I'm Sbu Mbatha and I'm an organic chemistry PhD researcher looking at how nature makes antibiotics. This is going to be a virtual tour of how to use IR spectroscopy, and I hope you enjoy this video.
IR spectroscopy is an analytical technique that chemists use to identify functional groups present in a compound and therefore help us to determine the structure of products synthesized in the lab. It's important to note that no one technique tells you everything you need to know about the compound, but a combination of different techniques such as NMR spectroscopy, mass spectrometry, to name just a few, can be used to identify a compound. Please visit the Bristol Chem Labs channel to find out more about these techniques. Bonds within molecules vibrate at temperatures above absolute zero, and there are several modes of vibrations that allow absorption in the infrared region. Some examples of these vibrations include bending and stretching, as illustrated here for water. These bonds vibrate with different amounts of energy at frequencies which depend on the mass of the atoms and the length and strengths of the bonds. If the vibration of these bonds results in a change in dipole moment, then the molecule will absorb infrared energy at a frequency corresponding to the frequency of the bond's natural vibration. So how does it work? Infrared spectrometers work by passing infrared radiation across the frequency range through a sample, and a detector is used to measure the absorptions made by each type of bond in the compound. The most commonly used IR technique is Fourier transform infrared spectroscopy, which uses a system called an interferometer. This consists of a source of radiation, a sample compartment, beam splitter, mirrors, laser, and a detector. The source energy goes to the beam splitter, which splits the beam into two parts. One part transmitted to a moving mirror and the other reflected to a fixed mirror. The two beams are reflected from the mirrors and recombined at the beam splitter. When the beams are combined, an interference pattern is created, called an interferogram. This then goes from the beam splitter to the pre-prepared sample, where some energy is absorbed and some is transmitted. The transmitted portion reaches a detector which reads information about every wavelength in the infrared range. The detector signal is then sent to the computer, where it is Fourier transformed to convert the interferogram into a spectrum. A background single beam is also collected in the absence of a sample, which is ratioed with the sample single beam to produce a spectrum of transmittance against decreasing wave number. IR spectra are quite distinctive and easy to identify. Here is an example spectrum of ethanol. The large troughs are a result of particular bonds in the molecule absorbing radiation, allowing for functional groups to be identified. The spectrum can conveniently be split into four regions for interpretation. From 4000 to 2500, you get the absorption of single bonds to hydrogen, for example, CH, OH, and NH single bonds. From 2500 to 2000, you get the absorption of triple bonds, so carbon-carbon, triple bonds, and carbon-nitrogen triple bonds. From 2000 to 1500, you get the absorption of double bonds, for example, carbon-carbon double bonds and carbon-oxygen carbonyl bonds. And from 1500 to 400, you get the absorptions owing to other bond deformations, and this is usually called the fingerprint region. In the case of ethanol, 3 sample absorptions have been picked to show you the bond vibrations which produce them. In yellow, we have the energy absorbed by OH stretching. In purple, CH bond stretching, and in red, CO bond stretching. A more advanced example of FTIR that will be demonstrated in this video is called Attenuated Total Reflection, or ATR infrared spectroscopy. This method allows for samples to be examined directly in the solid or liquid state without advanced preparation. A beam of infrared light is passed through an ATR crystal, such as diamond, in such a way that it reflects at least once of the internal surface in contact with the sample. This forms an evanescent wave, which extends into the sample. As it exits the crystal, the beam is then collected by a detector before the signal is Fourier transformed to give a spectrum. With liquid samples,
This is the
a shallow
ATR
amount enough to cover
spectrometer
the
here at
surface
the
of
University
the
of Bristol
is
Teaching Lab,
sufficient.
which we'll
However,
be using to
with a solid
demonstrate.
sample, it has to be firmly clamped and compressed
The
into
crystal
direct
surface
contact
is first
with the
cleaned
crystal
by
so that
wiping with
trapped
an
air
alcohol
does not
wipe.
distort the spectrum.
The
Using
compression tip
infrared
is removed
spectroscopy
and
to help
cleaned before
elucidate the structure
reattachment
of
to
a
the pressure
compound
tower.
is a useful tool, as no two organic
The
compounds
solvent
have
is
the
left
same
to
spectrum.
evaporate and dry
Hence,
before
a
loading the
compound can be
sample.
identified with certainty
Once
by
dry,
comparing
a
to
background
a
scan
pure
is run
compound.
to ensure that any
As
background
such,
molecules are
IR
detected and
spectroscopy
removed
has
from
many
future scans.
applications, such as quality control of pharmaceuticals and wine production. It's also widely used in
Once
law
background
enforcement,
scan is
for
run,
example,
a small
in
spatula
breathalyzers
of the
and in
compound
drug
is deposited,
identification.
making sure to cover the entire crystal. You can then click to scan the sample. As the initial scan is taken, the sample is compressed using the pressure tower to ensure good contact of the crystal and the sample. The sample is then scanned several times, producing the spectrum for the sample being investigated. The spectrum is given as percentage transmittance against wave number. When the scan is complete, the troughs are labelled and the sample is named. When finished, the spectrum can then be printed to keep as a record. The spectrometer is then thoroughly cleaned after use with an alcohol wipe, remembering to remove and clean the compression tip too. Liquid samples can also be directly analysed by pipetting a small amount onto the surface of the crystal without the need to compress it. As previously mentioned, no two spectra are the same, and hence IR can be used to identify unknown products of reactions. In this example, we've done an oxidation reaction from a secondary alcohol to a ketone, and we can compare the spectra to determine whether or not the reaction was successful. After scanning the reaction sample, the two spectra can be overlaid to check for similarities and differences. For propanone, you can see the loss of an OH trough and the appearance of a carbonyl trough, which indicates the reaction was successful.
I hope this video was useful. If you've got any questions, then please get in contact. Thank you.